Welcome to this lecture on collapsible, determinate, and indeterminate frames. Before we look at some problems, I would like you to refresh some of the fundamentals. One of the things that I want to talk about here is identification of two force members. What are they and what is their special property? Let's say you have a two force member like this, and two forces F1 and F2 are acting on this member. Now this member should be in equilibrium. So if we balance the moment at point B, the moment due to F2 is automatically 0 because F2 passes through B. For the moment from F1 to be 0, the perpendicular distance between B and F1 should be 0. That means F1 also passes through B. Now let's balance the moment at point A. F1 passes through A. Then the moment due to F2 at B should be 0, which means that the force F2 must also pass through B, which means that the forces on a two force member F1 and F2, they act along the line joining points A and B. Now the moment is balanced. So for force balance, F1 must be equal to F2. So a property of a two force member is that the two forces pass along the line joining the 2 points of application, and the forces are equal. Let's identify some two force members on these structures. On member A, B, C, there are three forces, one coming from the pin at A, one coming from the pin at B and plus the load, one coming from pin at C plus the load. So ABC is not a two force member. However, CD is a two force member. There is a force at C and there is a force at D. So it's a two force member, and the two forces must pass along the line CD, and those two forces must be equal. Similarly, BD is a two force member, ED is a two force member. On this diagram, again, BE is a two force member, force at B, force at E. ED is a two force member, CD is a two force member. Here CBD is not a two force member because there is a force at pin C, a force at pin B, and a force at pin D. AC is not a two force member, force at pin C, an applied load, and force at pin A. However, AB is a two force member because there is a force at A and a force at B, and the forces at A and B are equal, and they must pass along the line AB. Okay, now we have pinned down this idea of two force members, and now let's look at some structures. And we will use the concept of two force members. Let's build a structure using the free body diagram software from Actus Potentia. In this software you have a empty workspace, and there are some tools at the top, and as I solve 2 or 3 problems you will know how these tools are used. So let's select a straight member, bring it down. Let's select another straight member, bring it down. Put these two ends together, and we will take a pin joint and attach it here. So now we have this structure ABC. Now we need to support them. At C, I am going to put a pin, and at A, I'm going to put a roller. So now our structure is built. Now we are going to apply a force on this structure. So click on this button. This is a force couple tool, and apply it on member BC. You have several choices: distributed force, couple, point force. So let's apply point force. As you can see, by default the force is applied at B, but I want to move it somewhere in the middle. So I would change the distance between the force and the B, which is right now at 0, change it to 10. So the force goes to the middle. Now I want this force, instead of being vertical, I want this force to be horizontal. So now I'm going to use this degrees rotated utility to turn the force. And then click accept. So now we have a structure with a horizontal loading on this. And now we want to solve this structure, and before that I have to draw free body diagrams. So to draw free body diagrams, I use this tool. As you can see, it says exploded view, solve free body diagrams. Let's see what happens if I look at the exploded view. I immediately get a message that says this structure is not statically stable. So let's go back to this structure again, and let's see why that is the case. As you can see, that when we applied any load on this structure, this roller will begin to roll right, left, and the structure would collapse. That is the intuitive explanation why the structure is not stable. That any loading will make this roller roll and the structure collapses. Now let's look at some mathematical reasons. Now this member AB from our previous discussion is a two force member. So there are two forces, one at B, one at A, and those forces should be equal and should be along the line AB. But this roller can apply only a vertical force. It cannot apply a force along the line AB. That's why this structure collapses. Let's make a modification. So we will remove the roller. So take this delete object button and delete the roller and put a pin joint also. I'm sorry, we need a pin support, not a pin joint. So we put a pin support here. And now what happens is that this pin actually can apply force in any direction because this pin applies two components, horizontal and vertical, and this horizontal and vertical components can rearrange among themselves, so the support force is along AB. So this structure should be solvable. So let's go here. This is the free body diagram. I clicked on the whole FBD. And this is the free body diagram. Two forces coming from the pin on the right, two forces coming from the pin on the left. So there are three equations and four unknowns. You can write for this free body diagram three equations equilibrium, two force balance equation and one moment balance equation. So we have three equations, but there are four unknowns. So as such, when I look at this whole free body diagram, I cannot determine these forces. So we have to look into some details. So if you look at member AB, member AB is two force. So actually at this point, although the whole body FBD shows two forces, but actually we have only one force which is along the member. Let's look at the free body diagram of the other member. We have this force from Newton's third law coming from the two force member right here. So now what do we have is 1, 2, 3 unknown forces, and we can calculate those three unknown forces as three equations and three unknown forces. Let's put the structure back together and make another modification to it. So take a straight member, bring it here, and attach this member with two pins. This kind of a structure is generally called as an A-frame because it looks like the letter A. And when you look at various structures, you will see that many structures are combinations of this A-frame. Let's see what happens here when we add this member ED in the middle. So this is exploded view. And now it's coming back and saying the structure is partially unsolvable. Why is that? As before, the whole free body diagram has three equations and four unknowns. Two force balance equation, one moment balance equation, but four unknowns. Let's look at some of the details. Let's look at the member that we added, which is the horizontal member. It's a two-force member. It's connected to one arm, left arm of A, right here, and this end is connected to the right arm of the A, right here. Let's look at the left arm. So now this has become, this is no longer a two-force member because there is a two-force member attached here. So this becomes a multi-force member. So we cannot say the forces are along the member. So now how many forces do we have? 1, 2, 3, 4, 5, and 5 unknown forces and only 3 equations. How about the member on the right? We have again 3 equations and 5 unknown forces. And member DE has 1 and 2 forces. So none of these free body diagrams are solvable because we have more unknown forces than equations. So that's why this structure is unsolvable. Let's put the structure back together and do one thing to fix the unsolvable problem. We will keep the A-frame, but we will remove this pin. And replace this pin with a roller. Again, this is an A-frame, but this A-frame differs a little bit from the previous A-frame. The previous A-frame had pin, pin. Now we have pin roller. Now let's see what happens. So now what we have, this is the free body diagram of the entire A-frame. These two forces are coming from the pin. This force is coming from the roller. That's why it's marked as AN, normal. We can solve this A-frame because it has 3 equations and 3 unknown forces. So remember that this vertical force from the pin is now known. So this vertical force from the pin is now known. So let's look at the free body diagram of the left arm. So now it says 3 equations and 4 unknown forces. Not true, because from the whole free body diagram we have calculated this. So this is the starting point for solving the A-frame problem. After we get this vertical force AN, then we go to ABE. Now AN is known, and we can calculate from 3 equilibrium equations. We can calculate this force and this force along X and Y component. This is the force coming from the horizontal member, which is 2 force. So AN was calculated in the previous step. We calculate this force, and this force, 3 forces from 3 equations. So now this force from the horizontal member is now known. And then we go to the right member. This force from the horizontal member is known. These 2 forces, F1bx and F1by, actually are known from here, 0bx and 0by, because this force pair and this force pair is connected by Newton's third law. So in this free body diagram, actually everything is known because we calculated these from Newton's third law, and this free body diagram, this force we have calculated from the whole free body diagram, and this force we have calculated from the two force member. So now the problem is solved. So we went through three things: collapsible member, that is, if we move this, collapsible. If we move the roller, replace that by a pin, this structure is okay. However, excuse me. If we do this, too many unknowns, you cannot solve it. This structure is okay too. So collapsible, determinate, and indeterminate structures. That concludes this lecture. Thank you for listening.